Introduction. Akash, do you know about the composition of gases in air? Yeah, air is a mixture of approximately 79% of nitrogen and 21% of oxygen. Good, you are right. But there are also some other gases present in the air. These gases are known as noble gases. Noble gases are present approximately 1% in air. Okay, and what are the names of these gases? Neon, argon, krypton, and xenon, all together known as noble gases. Akash, don't you know that these elements are the members of P block in the periodic table? No, I don't know, but I want to know more about it. Fine, let's move to understand more about P block elements. Students, now we will study about the 17th and 18th group of the P block elements.
Objectives. At the end of this lesson, you will be able to define group 17 elements, explain physical and chemical properties of group 17 elements, describe halides and oxides of group 17 elements, analyze anomalous behavior of fluorine, explain manufacturing and properties of chlorine, know about interhalogen compounds, define group 18 elements, explain physical and chemical properties of group 18 elements. Group 17 elements, the halogen family. The non-metallic elements fluorine, chlorine, bromine, iodine, and astatine constitute group 17 of the periodic table. Their salts are present in seawater and hence they are collectively known as halogens. The general electronic configuration of halogens is Ns2np5. They have a very strong tendency to acquire stable inert gas configuration by accepting one electron. For this reason, halogens exhibit non-metallic behavior. Astatine, the last member of halogen family, is a radioactive element with a very short life. General trends in properties. Atomic and ionic radii. Atomic and ionic radii are small and increase regularly down the group from fluorine to iodine because new electronic shells are added. Ionization enthalpy. Ionization enthalpies of all halogens are very high. Therefore, they have a lesser tendency to lose electron. However, this tendency increases down the group because the distance of valence shell from nucleus increases. Electronegativity. They have a very high electronegativity. It decreases down the group. Fluorine is the most electronegative element in the periodic table. Electron affinities. They have high values of electron affinities. On moving down the group, electron affinity values decrease because size of the atom increases. A low value of electron affinity for fluorine is due to the small size of fluorine atom. In a compact 2b subshell of fluorine, the added electron does not feel much attraction, resulting in low value of electron affinity. Physical properties of group 17 elements. Melting and boiling points. Melting and boiling points increase with increase in atomic number. This indicates that the strength of intermolecular forces of attraction between the molecules increases with the increase in atomic number. Physical state. The halogens are all diatomic and exist as F2, Cl2, Br2, and I2. The intermolecular forces are very weak in halogens. The nature of forces in van der Waals and their magnitude increases down the group. Thus, F2 and Cl2 are gases, bromine is a volatile liquid, and iodine is a volatile solid. Color. The color of the halogen is due to absorption of visible light by their molecules, resulting in the excitation of outer electron to higher energy levels. The color deepens down the group. Oxidation states of halogens. All the elements of the halogen family have a tendency to acquire noble gas electronic configuration by either accepting an electron resulting in the formation of monovalent anion or by sharing one electron with those of the other elements. Thus, they show an oxidation state of -1 or +1 depending on whether the element combining with halogens is less electronegative or more electronegative than halogen. Fluorine is the most electronegative element, and it always has -1 oxidation state and never has a positive oxidation state. Also, higher oxidation states are not possible in fluorine as it does not have vacant d orbitals. Other elements of this group show oxidation states of +1, +3, +5 and +7. Higher oxidation states of these elements are due to the presence of vacant d orbitals. Chemical properties of group 17 elements. Some important trends in the chemical reactivity of the compounds of these elements are following. Hydrides. Halogens combine with hydrogen to form volatile halides of the formula HX. Except HF, all other hydrides HCl, HBr, HI are gases. HF is a liquid because of intermolecular hydrogen bonding. The bond between hydrogen and halogen is covalent in all the cases. All the hydrogen halides act as acids in their aqueous solutions. All the halogen acids ionize to give H+ ion and halide ion X-. The reducing character of the hydrides increases down the group. It is because the strength of HX bond decreases from HF to HI. Halides and group 17 elements. The halogens react with almost all the metals and non-metals. With metals having low ionization energies, the halogens react to form ionic halides which have got high boiling and melting points. As the electronegativity of the halogens decreases down the group, the ionic character decreases. For example, SnCl2 and PbCl2. With metals having high ionization energies, the halogens form covalent halides, for example, SnCl4 and PbCl4. With nonmetals, the halogens readily form covalent halides, for example, PF5 and PCl3. Oxides of group 17 elements. Halogens do not combine with oxygen directly. For example, oxygen difluoride OF2 is prepared by action of fluorine on 2% sodium hydroxide solution. The compounds of oxygen with fluorine are called fluorides because fluorine is more electronegative than oxygen. Most of these compounds are endothermic and unstable and are likely to explode, resulting in the formation of more stable products. Among oxides of each halogen, the higher oxides are relatively more stable. All of the oxides are powerful oxidizing agents and decompose explosively when subjected to mechanical shock or heat. Anomalous behavior of fluorine. Fluorine has very small size, very high electronegativity, high ionization enthalpy, and no d orbitals in its valence shell. It exhibits some different behavior from other elements in following ways. Bond dissociation enthalpy of F2 is low. Therefore, F2 is very reactive. The compounds of fluorine have maximum ionic character. The hydride of fluorine is liquid due to molecular association by intermolecular hydrogen bonding. It always shows an oxidation state of -1. It does not form polyhalide ions due to the absence of d orbitals. Chlorine. Chlorine is too reactive to occur in uncombined state in nature. It is widely distributed in combined state as chlorides of Na, K, Ca and Mg. It is usually prepared by heating concentrated HCl with MnO2. It can be prepared by heating a mixture of NaCl and concentrated H2SO4 with MnO2. The gas is passed through water to remove HCl and then dried by passing through concentrated H2SO4. Pure chlorine gas is obtained by dropping concentrated HCl over solid KMnO4. Manufacturing of chlorine. Commercially, manufacturing of chlorine is done by the following methods. Decans process. In this process, hydrogen chloride gas is oxidized with air in presence of cuprous chloride catalyst at 723 Kelvin. It is also manufactured by electrolysis of fused NaCl using lead as cathode and carbon as anode. Chlorine is also obtained as a byproduct in the manufacture of NaOH either by Caster-Kellner or by Nelson's process. In this reaction, a saturated solution of NaCl in water is electrolyzed. Properties of chlorine. It is a greenish-yellow colored gas with a characteristic pungent and suffocating smell. It is moderately soluble in water and forms a pale yellow solution which smells of chlorine. This solution is called chlorine water. In dark there is no reaction, but when a mixture of H2 and Cl2 is exposed to sunlight, reaction takes place with explosion. On heating, it directly combines with a number of elements. It is a good oxidizing agent. In presence of moisture, it acts as a strong bleaching agent. It reacts with organic compounds. With saturated components, substitution takes place. But with unsaturated compounds, addition reactions take place. Uses of chlorine. The important uses of chlorine are following. It is used in the extraction of metals like gold and platinum. It is used in the manufacture of poisonous gases like phosgene and mustard gas. It is used in the manufacture of CHCl3, CCl4, PVC, DDT, and BHC. It is used for sterilizing water for industrial and domestic uses. It is used for extracting bromine from bromides. It is used as a bleaching agent for vegetable and organic matter. Hydrogen chloride. In 1648, Glauber obtained hydrogen chloride by heating common salt with concentrated sulfuric acid. It is a colorless gas with a sharp penetrating smell and acidic taste. It is extremely soluble in water. 1 volume of water dissolves about 450 volume of hydrogen chloride under ordinary conditions. It can be easily liquefied to a colorless liquid or frozen to colorless solid. In laboratory, it is prepared by heating chlorides with concentrated H2SO4. Hydrogen chloride is dried by passing it through concentrated H2SO4. It is used in the manufacture of Cl2 and NH4Cl, in the extraction of glue from animal tissues and bones, in pickling of steel, and as laboratory reagent. Properties of hydrogen chloride. It readily combines with ammonia, producing white dense fumes which consist of solid particles of NH4Cl suspended in air. It combines with many metals, especially on heating, giving chlorides. It reacts with basic oxides to form chlorides and water. The aqueous solution of hydrogen chloride is called hydrochloric acid, which acts as a strong acid. It decomposes salts of weaker acids. With soluble salts, corresponding chlorides are precipitated as a white precipitate. Oxoacids of halogens. Fluorine yields only one oxoacid, hypofluorous acid. Chlorine, bromine, and iodine form 4 series of acids with formula HOX, HXO2, HXO3, and HXO4. Many of these are known only in solutions or as salt. The structures of oxoacids of chlorine are hypochlorous acid, chlorous acid, chloric acid, perchloric acid. The acid strength of oxoacids of the same halogen increases with increase in oxidation state of halogen. For example, the acid strength of different oxoacids of chlorine is in the order among oxoacids of different halogens having same oxidation number. The acidic strength decreases with increase in the size of halogen. For example, acidic character of hypohalous acid series is in the order: greater the size of halogen atom, lesser will be its electronegativity, and hence lesser will be the acid strength of the acid. Interhalogen compounds. The compounds containing 2 or more halogen atoms in their molecules are known as interhalogen compounds. Their general formula is AXN, where A is less electronegative halogen and X is more electronegative halogen, and N is its number. The oxidation state of halogen A may be +1, +3, +5, and +7. Therefore, there are 4 types of interhalogen compounds: AX, AX3, AX5, and AX7. All these can be prepared by direct combination or by the action of a halogen on a lower interhalogen. They are covalent compounds. They are more reactive than the constituent halogens. They are very good oxidizing agents. Their melting and boiling points increase with the increase in the difference of electronegativity. Structure of interhalogen compounds. The molecular structure of interhalogen compounds can be explained on the basis of VSEPR theory. Structure of AX type of interhalogens is linear. The central halogen atom assumes sp3 dehybridization in AX3, which has a trigonal bipyramidal arrangement. sp3 d2 hybridization in AX5, which has octahedral arrangement. sp3 d3 hybridization in AX7, which has pentagonal bipyramidal arrangement. Interhalogen compounds can be used as non-aqueous solvents and are very useful fluorinating agents. Group 18 elements, noble gases. The elements helium, neon, argon, krypton, xenon, and radon constitute group 18 of the periodic table. The general outer electronic configuration of these elements is Ns2np6. They have 8 electrons in their valence shell except helium, which has only 2 electrons. All of these are gaseous under ordinary conditions of temperature and pressure. They are highly non-reactive and do not take part in chemical combinations to form compounds, therefore also called inert gases. Physical properties of group 18 elements. Atomic radii. In noble gases, the atomic radii corresponds to van der Waals radii. As we go down the group, the van der Waals radius increases due to the addition of new electronic shells and increases in screening effect. Ionization enthalpy. The ionization enthalpies of noble gases are very high. This is due to the stable configurations of noble gases. It decreases with increase in atomic number from helium to radon. Electron gain enthalpy. Since noble gases have stable electronic configurations, they have no tendency to accept the electron and therefore have large positive values of electron gain enthalpy. Boiling point and melting point. On moving down the group, boiling points and melting points of these elements show a gradual increase due to corresponding increase in the magnitude of the van der Waals forces of attraction. Chemical properties of group 18 elements. The noble gases are generally inert and do not participate in the reactions easily due to stable closed-shell electronic configurations. Noble gases are only slightly soluble in water. The solubility increases down the group. Except helium, all other noble gases are absorbed by coconut charcoal at low temperatures. It is extremely difficult to liquefy these gases. Ease of liquefaction increases down the group from helium to radon. The noble gases remain unaffected by acids, alkalis, oxidizing agents and reducing agents and do not form compounds. Compounds of xenon. Xenon forms 3 fluorides, XeF2, XeF4 and XeF6. These can be obtained by the direct interaction between xenon and fluorine under appropriate experimental conditions. The oxide and oxyfluorides of xenon are obtained from fluorides. Xenon trioxide can be obtained by the hydrolysis of XeF4. The oxyfluorides of xenon are xenon oxydifluoride, XeOF2, and xenon oxytrifluoride, XeOF4. XeOF2 is obtained by the partial hydrolysis of XeF4. XeOF4 is obtained by the partial hydrolysis of XeF6. The fluorides of xenon react with fluoride ion acceptors to form adducts in which the fluorides change to cationic species, whereas the fluoride ion acceptors form fluoroanions. Uses of noble gases. The important uses of noble gases are the following. Because of lightness of helium, it is used in inflating aeroplane tires. A mixture of oxygen and helium is used in treatment of asthma. Helium is used to provide inert atmosphere in melting and welding. Neon is used for filling discharge tubes, which have characteristic colors and are widely used for advertising purposes. Neon is also used in beacon lights for safety of air navigation as the light possesses fog and storm-penetrating power. Along with nitrogen, argon is used in gas-filled electric lamps because argon is more inert than nitrogen. Krypton is used in high-efficiency miner's cap lamp. Xenon is used in xenon photographic flash tubes. Radon is used for the treatment of cancer and other diseases. Did you know? Halogen lights floodlight a stadium at night, allowing large audiences to watch. Chlorine salts are often used to the water in swimming pools to kill bacteria, giving the water a greenish-blue tinge. Fluorides are often added to the drinking water to prevent tooth decay. Summary. Let us summarize what we have learnt. The non-metallic elements fluorine, chlorine, bromine, iodine and astatine constitute group 17 of the periodic table. The halogens are all diatomic. The nature of forces of van der Waals and their magnitude increases down the group. Fluorine is most electronegative element and it always has -1 oxidation state and never has a positive oxidation state. The compounds of oxygen with fluorine are called as fluorides. The acid strength of oxoacids of the same halogen increase with increase in oxidation state of halogen. The compounds containing 2 or more halogen atoms in their molecules are known as interhalogen compounds. The elements helium, neon, argon, krypton, xenon and radon constitute group 18 of the periodic table. The noble gases are generally inert and do not participate in the reactions easily due to stable closed shell electronic configurations.